All right, I'm going to begin on problem 2. Given mass flow rate of an ideal gas flows through an adiabatic compressor. So this time we have mass flow going through the system, so we need the open system equations. It's operating at steady state, it has an adiabatic efficiency. We don't know what the gas is, but it has a molecular weight that's given and a specific heat ratio given. The pressure and temperature are given at the inlet, the exit pressure is given, and we're going to assume constant specific heats this time. So the first thing I'm trying to do is find the exit temperature if the compressor process was isentropic, because in order to find the actual temperature, I'm going to need to do that first. So the easiest thing to do is for constant specific heats. So if get my pen here. If CP is constant, CV is constant. Sorry, that's a little ugly. CV is constant, then I have some equations that I can use on my equation sheet. So I'll bring those up here, booklet. I go to the top again. Jump to the top. So for constant specific heats for an isentropic process, which I'm going to assume first off, I can use this equation here that the temperature ratio is related to the pressure ratio, or the temperature ratio is related to the ratio of volume. So I'm going to use this one so that T2 equals T1 P2 over P1 to the K minus 1 over K. And that simply comes from this expression where delta S equals 0, actually the second one here. So if it's isentropic, then this equation simplifies down to this. So it's an ideal gas. I'm going to assume it's isentropic, constant specific heats, so these equations then apply. Going back to the problem. It's one of these here. Okay, so it's a little bit in our way there, but so my final temperature, the exit temperature then will be T2. So I'm going to use T1 is 40 degrees C, but I need to put it in absolute temperature. So T2 plus 273 equals T1 plus 273. Since I'm working in degrees C, but I need in the equation to have degrees Kelvin, or 273.15 to be exact. 4.45 is P2 divided by 1.35 is P1, and my specific heat ratio K is 1.34, so 0.34 divided by 1.34, and if I do that and put in T1, which is 40, I'll end up with solving for T2 in degrees C, which will give me 166.49. Of course, this will be, when I solve the right-hand side, will be 273 degrees larger than that because it's in Kelvin. So after I calculate the right-hand side, I'll subtract 273 from it, which should give me this. All right, now to find the actual temperature, I'm going to use the isentropic efficiency. And the isentropic efficiency for the compressor is 87.5%. And the isentropic efficiency is the actual work actually for a compressor, it's going to be the ideal divided by the actual. Which the ideal work is going to be m dot delta H ideal, which is going to be H exit S minus H inlet S, and mass flow rate, same for ideal and actual, but it's going to be HE minus HI. Sorry, I put an S there, I didn't mean to. It's the ideal process, but the enthalpy at the inlet is the same, since that's a fixed given condition. So I know this. I can write the enthalpy change, since the definition of specific heat is dH dt for an ideal gas. And then if Cp is constant, I can integrate this, and I'll get that dH equals Cp dt. I can integrate both sides. Since specific heat is constant, I can bring that outside the integral, and I get that delta H equals Cp delta T. So bringing that up to this equation, I get m dot Cp T exit for the ideal case, the isentropic case, minus T inlet, divided by m dot Cp, the actual exit temperature with the isentropic efficiency, minus the initial temperature, or inlet temperature. So in this case, I can solve using this equation for T exit, since the m dot cancels, the specific heat cancels. I just found T exit, T inlet was 40 degrees. So this is 40 degrees. This is 166.5. And T exit then is what I'm solving for. And in this case, I can use degrees C, since I'm doing a temperature difference. If I add 273 to both, it doesn't make any difference. You can do that if you want. And then I will end up with a temperature, actually, I was reading the wrong one. T exit is 150.6, so this is not 160, it's 150. But now, using 150 in this expression, I will get 166.5. Okay, the specific heat, how would I find that? Specific heat equals dH dt, but I don't have tables because I don't know what the gas is, and plus I'm using average specific heats. So let's scroll up here a little bit. So it says use constant specific heats, but I was given a few other things. I was told what R is, or actually molecular weight, and the specific heat ratio. So K equals Cp over Cv, and R equals Cp minus Cv. And I have values for, I have a value for K. R equals R bar divided by the molecular weight. So R would be, for this gas, would be 8.314 divided by 28.5. And that would have units of kilojoule per kilogram Kelvin. Then this is equal to 1.34. This is equal to 8.314 divided by 28.5. And I've got two equations and two unknowns. The easiest way to solve that would be solve the first one for CV. So CV equals CP divided by 1.34, and then write the second one as 8.314 divided by 28.5 equals CP minus CP over 1.34, or CP times 1 minus 1 over 1.34, and then solve for CP. And if you do that, you should get 1.1497. Okay, the rate of heat transfer for the compressor. It's an adiabatic compressor operating at steady state, so the heat transfer is 0 because that's what adiabatic means. So Q equals 0 because it's adiabatic. And then finally find the power input for the compressor. So I had that written a moment ago, but erase this. There we go. Okay, so the work we found was m dot times delta H, and which is m dot CP delta T, which was T exit minus T inlet. We found the specific heat, we found the temperature, we were given m dot, and so then we're given the inlet temperature, and so we can solve for the work, the power, W dot. And we get 0.4121. Of course, the units dependent on, we want it in kilowatts, so we have m dot in kilograms per minute times specific heat, which is kilojoule per kilogram Kelvin. Even if we use degrees C, the temperature difference in Kelvin is the same as in degrees K, so we're going to have, either way we do it, we're going to have degrees in Kelvin. So Kelvin will cancel, kilograms will cancel, and we'll get kilojoules per minute, so we need to multiply by 1 minute is 60 seconds, and so we'll have the minutes cancel, and we'll have now kilojoules per second, which, and 1 kilowatt is 1 kilojoule per second, and so seconds cancel, kilojoules cancel, and left with kilowatts. So I get 0.4121 kilowatts, or approximately 0.17 times specific heat, which is 1.1497 times 166.5, approximately minus 40, and then times 1 over 60